I'm Richard Reyes, CEO of NLinkIT. Let's begin. If you don't like network slowdowns, but you still need efficiency, then consider OSPF areas. Understanding OSPF areas is crucial for any network engineer. They reduce the size of the routing database that each router needs to maintain. Instead of knowing the entire network topology, routers focus only on their area. This means less information to process. Additionally, OSPF areas reduce overhead traffic. By segmenting the network, the number of link state advertisements is minimized. For larger networks, multi-area OSPF offers scalability and more efficient management. You get a network that can grow without becoming unmanageable. Faster convergence is another advantage. When changes occur, the network adapts more quickly, which increases stability. Finally, OSPF areas help reduce processing and memory needs. By minimizing LSA exchanges, your routers work smarter, not harder. Optimize your network's performance with OSPF areas. They are essential for efficient operation in large-scale environments. Optimize with OSPF areas. In previous videos we worked on basic OSPF configuration, but today we will talk about a very important topic called OSPF areas. For this, I want you to keep in mind that this video is the continuation of my previous video, basic OSPF configuration. Alright, let's access the routers, and I'm going to show you something that is common among these routers. I'm referring to R1, R2, and R3. First of all, let's access R1, go to Routing OSPF areas. And here we find OSPF area 0 with the area ID 0.0.0.0. We can also find the router interfaces participating in this OSPF instance. Observe that they all belong to area 0. Now let's access R2. Routing OSPF areas. And here we find OSPF area 0. The area ID is 0.0.0.0. And here we have the router interfaces participating in this OSPF instance. We can see here that they all belong to area 0. In router 3, exactly the same thing happens. All its interfaces belong to area 0. Now, to better address this topic, I'm going to modify the topology image without changing anything in the configurations we have from the previous video. What I intend to do with these changes is express or show that all of this belongs to area 0. Here, in this yellow circle, we have area 0, which is everything we had already worked on in previous videos. We have the names of the router interfaces. Over here we have the network segments of each link, and we have the IP addresses of each interface. For example, for this link, the network is 172.168.1.0/30. Then the Ether2 interface of R1 will have the IP address 172.168.1.1, and on that same link, the Ether1 interface of R2 will have the IP address 172.168.1.2. For space reasons, only the number of the last octet is denoted, and we use this same logic for the rest of the topology. We have also added 2 more areas. Over here we have area 1 with its 2 routers, R4 and R5, each with its respective LAN. And over here we have area 2 with its 2 routers, R6 and R7, each with its respective LAN. There are some basic things that we have already done in previous videos, and therefore I don't think it's necessary to include them in this video. All this I do to make the learning process faster. The configurations that I have already prepared on all the routers we are going to work with in this video are: number 1, assign the name to the routers in Winbox. That's very simple, we already have that done. Number 2, label the interfaces of the new links. I also already did that off camera. Number 3, the configuration of the IP addresses. This is simply putting the IP address according to how the topology is labeled. Number 4, configure the router ID for R4, R5, R6, and R7. Remember that we had already done this for R1, R2, and R3, so we are not going to repeat that process here. But I already did that configuration on these routers, R4, R5, R6, and R7. I put its respective router ID on each one. And the other thing I prepared, point number 5, that I configured the DHCP server so that the LAN of each router has a dynamic IP address. We had also done this previously, so I didn't include it in this video, but those configurations are already set on the routers. Alright, and knowing that we have this prepared, now we can focus on the configuration of the entire basic OSPF process and the topic of multi-areas. So let's go to the topology, and here we can see that R2 has a new link via Ether 3 with R4 and also has a new link via Ether 4 towards R5. It's important to observe carefully which area these interfaces are going to belong to or be connected to. In this case, these interfaces have connections towards Area 1. So let's access R2 routing OSPF, go to Areas. And here we find the only area that we had configured on that router. That is OSPF Area 0. So, click on the plus sign, name it, leave it like that, OSPF Area 1, and the area ID will be 0.0.0.1. Click OK. And here we see two areas already added, Area 0 and Area 1. Now let's go to Interface Templates. Click on the plus sign and let's map the new interfaces with Area 1. So, I select Ether 3 to R4. Select the area OSPF Area 1. Network type point-to-point. And we continue now with the whole security part. Authentication MD5. The key, let's copy the same one from previous videos. So I paste it. And the auth ID, we leave it at 255. Now we add the interface Ether 4 to R5. The network type will be point-to-point. And we are also going to configure the whole security part. And click OK. And it seems we forgot something very important here. Observe that we left the area in Area 0. But this interface belongs or is actually connected to Area 1. So let's correct that error. Select OSPF Area 1. Click OK. Here we can observe that these interfaces are connected to Area 0. But these two interfaces are connected to Area 1. Back to our topology, here we can see that router R4 has a link on Ether 1 connected towards R2, and another link on Ether 3 connected towards R5, and has the LAN connected to Ether 2. So with this information clear, let's configure the complete OSPF protocol. Remember that R4 is a new router in our topology, so access routing OSPF and create the instance and assign its corresponding router ID. Then go to Areas plus Sign and create OSPF Area 1. The area ID 0.0.0.1. Click OK. Go to Interface Templates and let's map the interface Ether 1 to R2 with Area 1. Network type point-to-point. And configure the security. Click OK. We are also going to add the interface Ether 2 to PC4 and check the passive option since a LAN will connect here and not an OSPF router. For the new routers in the topology, I am not going to add the loopback interface since this is only an optional step in case MPLS were to be used in the future, but that's not our case. So click OK. And finally, let's add the interface Ether 3 to R5. Network type point-to-point. Configure the security. And click OK. Observe all interfaces are mapped with Area 1. Now I must access R5, and we are going to do exactly the same process. Configure the instance. I am also going to configure the area. And now let's map all the interfaces to the corresponding area. Observe that all interfaces ended up mapped in Area 1. And here we can observe that R3 has two interfaces that connect with routers from Area 2. One of these is Ether 3 that connects with R6, and the other interface is Ether 4 that connects with R7. So let's access router R3 routing OSPF areas. Here we find area 0 that we had worked on in previous videos, but now we need to create area 2. So I click the plus sign. In name leave it OSPF area 2. The area ID will be 0.0.0.2. Click OK. Now let's go to Interface Templates. Plus sign, select Ether 3 to R6 and map it with Area 2. Network type point-to-point. And fill in the security part completely. Now click OK. Now we add the interface Ether 4 to R7 and map it with OSPF area 2. Network type point-to-point and complete the security fields. Click OK. Observe, this is how our two interfaces ended up mapped to area 2. Returning again to our diagram, here we observe that router R6 connects with R3 via the Ether 1 interface and connects with R7 via the Ether 4 interface, and on Ether 2 it has its LAN. So, let's configure OSPF on that router. Remember that this router currently has nothing created in OSPF, so let's start by creating the instance. Go to Routing OSPF, click the plus sign, and select its router ID. Click OK. Now I go to Areas and create Area 2 with its ID 0.0.0.2. Click OK. Then go to Interface Template. Click the plus sign and select Ether 1 to R3. The area will be OSPF Area 2. Network type point-to-point. And fill in the security part. Click OK. Now add the interface Ether 2 to PC6 and select this passive checkbox since this interface will connect the LAN. And finally, add the interface Ether 4 to R7, network type point-to-point, and fill in the security part. Click OK. Alright, all that remains is to configure the entire OSPF process on router R7. I won't intervene verbally since it's basically repeating the process we've done on the other routers. Alright, we have finished the process on R7. So now, with all routers configured, let's check that the adjacencies have been established in order to continue moving forward. So, let's go to R2, Access Neighbors, and here we observe the two adjacencies. One with R3 and the other with R1. We had already done this in previous videos and it was already approved. But what we do need to verify is the new stuff we've configured in this video. And here we can see the established adjacencies of R2 and its adjacency with R5 and R4. This is fine. Now let's access R3 neighbors. Here we can organize this by areas, and we can see the two instances established with area 0, the instances we did in previous videos. And over here we can also see the adjacency with R7 and R6, which is what we've configured today. We also need to access R4, go to Neighbors, and add the columns with the priority information. And here we can see that we have established adjacencies with R5 and R2. So let's continue checking the adjacencies on R5. Everything looks perfect. Let's continue with R6. Here we can see the adjacencies with R7 and R3. And finally, let's check the adjacencies of R7. Here we can see the communication with R6 and R3. Apparently everything is correct, but we have to do the connectivity test between all the PCs on the network. So, let's access the console of PC4. Type the DHCP command to ensure we can receive a dynamic IP address. And we need to ping all the PCs on the network. Let's ping PC1. This is responding well. Let's ping PC2. Responds well. Let's ping PC3, it's perfect. Ping PC5. Perfect. Ping PC6. Working okay. Ping PC7. Responds well. Let's also ping towards the internet. And as we have been able to observe, we have correct, stable communication from PC4 with all the PCs on the network, and we also have internet access. These tests are a bit extensive, but it's necessary to do them, so we are going to do the same tests on PC5. Now we know that PC5 has correct communication with all the PCs on the network and also has internet access. We have to repeat the test on PC6. Alright, now we know that PC6 has communication with all the PCs on the network, stable communication, and that it also has internet access. And finally, let's repeat the tests on PC7. We find that PC7 has optimal communication with all the PCs on the network and also has internet access. Truthfully, I thought about leaving the video here, but I think a key test would be to verify the redundancy of the network in case a communication link between the routers fails. The objective of all this is that OSPF can calculate and generate alternate routes to guarantee that everything is fault tolerant and also to be able to offer or guarantee a constant service to the clients of our network. So, let's verify this. Access PC7. Ping PC4. We see it responds well. And using the trace command towards PC4, we can see that it takes 5 hops to send a packet from PC7 to PC4. It's 5 hops. Now, based on this information, we can have clarity about the route the packets are following. Let's go to the topology to explain. Here. Observe, the packet leaves PC7, passes through R7 towards R3, then continues its path to R2 and finally continues towards R4 to finally reach PC4. But I would like us to see what would happen if this link between R3 and R2 were to fail. Let's check it by accessing R2. And let's disable the IP address that connects R2 with R3. But before that, I want you to observe that here we have the 4 established adjacencies. And when we disable the IP address, this adjacency here with R3 should end. So we disable the IP address and observe that the adjacency immediately disappeared, which means that this link is broken. There is no longer communication between these two machines. Now from PC7, let's repeat the trace command towards PC4. And observe that we have 6 hops instead of 5. And over here we see that one of the routes is via the IP address 172.168.3.1, If we look at it in the topology, we can analyze that now the packet's route will be taking the path towards R1, since the shortest path towards R2 has a failure. If I ping PC4 again, it should respond normally, and indeed, it is doing so. But if we return to the topology and try to generate another failure, it would be something very good. For example, breaking this adjacency between R2 and R4 to see what automatic actions OSPF takes. So, we disable the IP address and the adjacency is broken again. Back on PC7, let's do the trace towards PC4. And observe that now the packet must make 7 hops instead of 6. Here we can see this IP address 172.168.5.2. If we analyze it graphically, it's the IP address of the Ether1 interface of R5. Which is to say that now the path to reach PC4 from PC7 will be this path that I am pointing out there. Likewise, the ping we see is responding correctly. I would also like to access PC4 to be able to analyze this from another perspective. For example, let's ping towards PC7. It's working well. And if we do a trace towards PC7, we find that we have 7 hops, which is exactly equal to the number of hops from PC7 towards PC4. Which is to say that the packets are following the same route to go from PC7 to PC4, and vice versa. Now what we will do is enable the IP addresses again to recover the adjacencies and have everything return to normal. Alright, the adjacencies are re-established now. And back on PC4 we do the trace towards PC7, and what we have as a result is equal to what we had before simulating the failures. We also see that the ping responds normally, and this lab has been a complete success. Alright friends, this was the explanation of the topic of OSPF areas. Truthfully, I tried to make it as detailed as possible. I hope this content was to your liking. Remember to like and share this video. I'll see you soon, and thank you very much.